Okay, so this is live. Okay, so this is live. Well, it's live. All right. All right, let's go. So yeah, we're gonna continue with our. It's a bit blurry though. Maybe I'm not reaching it. Oh, I think we have this right quality. Okay, nice. So yeah, we're gonna carry on with our learning curve in terms of deep learning and mathematics. The reason why we're going through this is because to actually understand how AI works, we have to understand the mathematics and also try to understand how it computes its gradients. And I would like to, after we have learned all of this, I would like to create a visualization for you guys so you can see in a more visual manner on how AI works. I'm gonna decrease the volume of the Spotify music here. So yeah. So we're gonna carry on. I think I were on page 7. Is it 15,000? Okay. So yeah, this is basically a bit this is a bit algorithmic blueprint, I would say. Oh, someone is texting and stuff. Anyways, so this basically just calculates the sum and then a carry. And if I'm not mistaken, this is actually I think this is just a normal adder. My screen went black for some reason. So this is the normal adder, and in terms of bitwise algebra, and this is the equivalent structure in terms of deep learning and perceptrons. So you can create similar logic with perceptrons in terms of software, which is different. So yeah, can I remove this? And for this document, thank you. So one notable aspect network of perceptrons is that the output from the leftmost perceptron is usually twice as the input to the bottommost perceptron, because here we have 2 arrows. When I defined the perceptron model 1, I didn't say whether this kind of double output to the same place was allowed, but it actually isn't. It doesn't really matter. So we can basically, I think he's gonna, yeah. So he basically adds these 2 arrows together and then just write and add the weights together. So the weight is in total of -4. The weight before was -2 here. In these 2. So we just add them together and create like 1 arrow with the same weight, because the input from these arrows is the same. Then if we just add the weights, we get the same arrow, not error. So up to now, I've been drawing inputs like this: x1 and x2 as variables floating to the left network. So if it is conventional to draw an extra layer of perceptrons, the input layer. So this is quite good to know. We have, so this is the input layer and this is the output layer, but these are the hidden layers or the extra layers. And for some reason in AI sense, it's conventional to write the input as an extra layer of perceptrons, but they are technically still the same. It's the same input. So we're gonna do that as well. Now this is not like a real working network at all, because we don't know the weights and we don't know the outputs and the training and the evaluation stages as well. I'm gonna paint this just so we get like a fundamental idea of it. That is also good for me because I'm gonna probably make like a sum of the streams I do later, then where I will explain everything. So hopefully you guys are okay with this kind of content at the moment. Also, this helps me in my own career, so it probably will help you as well, I think. If you're interested. Not a lot of people are interested. They only want to use it and not understand it. Yes, I guess understandable. Conventional to paint input layer as the others. Right. Yeah, and also also you can add connections with the same input as long as you add the weights together. All right, so this notation for input perceptrons in which we have an output but no inputs, right? So in shorthand, it doesn't really actually mean a perceptron with no inputs. To see this, suppose we either have a perceptron with no inputs, the weighted sum would be this equation here, would always be 0, and so the perceptron would output 1 if b is greater than 0, and if b is less or equal to 0. And that is the perceptron would simply output a fixed value, not the desired value. X1 in the example above. It's better to think of the input perceptron as not really being a perceptron at all, but rather special units, which are simply defined to output the desired values, which makes sense. It's just an input. It's not a perceptron at all. The adder example demonstrates how a network of perceptrons can be used to simulate a circuit containing many NAND gates, and because NAND gates are universal for computation, it follows the perceptrons are also universal for computation. The computational universality or universality of the perceptrons is simultaneously reassuring and disappointing. It's reassuring because it tells us that networks of perceptrons can be so powerful, or as powerful as another computing device. But it's also disappointing because it makes it seem as though perceptrons are merely a new type of NAND gate. That's hardly big news. However, the situation is better than this view suggests. It turns out that we can devise learning algorithms which can automatically tune the weights and biases of the network of artificial neurons. This tuning happens in response to external stimuli without direct intervention by a programmer. These learning algorithms enables us to use artificial neurons in a way which is radically different to conventional logic gates. Instead of explicitly laying out a circuit of NAND and other gates, our neural networks can simply learn to solve problems, sometimes problems where it would be extremely difficult to directly design a convolutional circuit. So they are basically saying that they can create what is it called? Binary NAND gates in software, and then multiply the amount of NAND gates that is produced. So they essentially optimized for area in terms of hardware area, but in software instead. That's pretty cool. That's good to know. So neurons can behave like perceptrons is the better word for this. Yeah, it's quite funny actually. I have a very big eraser here. I don't know if you guys can see it, but it's super big. And it works really well. We're gonna move my keyboard a bit. Yeah. So we need the perceptrons. Perceptrons can have the same functionality. Functionality in terms of is it NAND? Yeah, never mind. NAND D gates, but the scalability of complexity potential, Jesus, potential is a lot better than hardware. So they basically create the same network in terms of hardware, but in software, and software is very scalable compared to hardware. Very interesting. But now I have a different kind of neuron. So we now going into sigmoid neurons. Learning algorithms sounds terrific, but how we can devise such algorithms for neural networks? Suppose we have a network of perceptrons that we would like to use to learn to solve problems or some problem. For example, the inputs to the network might be the raw pixel data from a scanned handwritten image of digits, and we would like the network to learn with weights and biases, so that the output from the network correctly classifies the digit. To see how learning might work, suppose we make a smallest change in some weight or bias in the network. What we would like is for this small change in weight to cause only a small corresponding change in the output from the network. As we will see in a moment, this property will make learning possible. Schematically, here is what we want. Obviously, this network is too simple and to handwriting recognition. But this kind of makes sense. So they basically just take the output and just input it into the module itself again, I think. Or, yeah, so it's output plus the change of output, right? Kind of makes sense. But is this what they call a sigmoid neurons? If it were true that a small change in weight or biases cause only a small change in output, then we would use this fact to modify the weights and biases to get our network to behave more in the manner we want. For example, suppose the network was mistakenly classifying an image as an 8 when it should be a 9. We could figure out how to make a small change in the weights and the biases so the network gets a little closer to classifying the image as a 9. And that would, we repeat this. Changing the weights and biases over and over to produce better and better output, the network would be learning. Okay. So basically they're just changing weights and biases over and over, just to get a better learning curve. The problem is that this isn't what happens when a network contains perceptrons. In fact, a small change in the weights or biases any single perceptron in the network can sometimes cause the output of this perceptron to completely flip, say from 0 to 1. That flip may then cause the behavior of the rest of the network to completely change in some very complicated way. So while your 9 might now be classified correctly, the behavior of the network on all the other images is likely to have completely changed in some hard to control way. That makes it difficult to see how to gradually modify the weights and biases so the network gets closer to the desired behavior. Perhaps there is some clever way to getting around this problem, but it's not immediately obvious how we can change or how we can get a network of perceptrons to learn. And that makes sense. We can overcome this problem by introducing a new type of artificial neuron called a sigmoid neuron. Sigmoid neurons are similar to perceptrons but modified so that small changes in their weights and biases cause only a small change in their output. That's a crucial fact which allow a network of sigmoid neurons to learn. Okay, so let's describe the sigmoid neuron. We will depict sigmoid neurons in the same way we depict perceptrons. So they have 3 different inputs for some reason. These inputs can also take on any values. So between 0 and 1. So for instance, 0.63 is a valid input for a sigmoid neuron. Oh, so normal neurons only take 0s and 1s, while these takes all the different values between 0 and 1. Okay. I thought that was a normal neuron, but apparently I've been looking at sigmoid neurons all the time. Okay, that's good to know. So normal neurons are trash. Apparently. I mean, it's a good realization, I guess. So, let's write that as well. Just like a perceptron, the sigmoid neuron has inputs, which is x1, x2, and so on. So there can be multiple inputs. It doesn't have to be 3 inputs. It can be like a lot of inputs. So let's make some dots here. But instead of being just 0 or 1, this inputs can also take on any values. Right, okay, so that's good to know. Between 0 and 1, by the way, just so we make that clear. 0 and 1. So we are talking about floating point numbers now. That's good. So for instance, 0.638 is valid input for a sigmoid neuron. Also, just like a perceptron, the sigmoid neuron has weights for each input. So we have also weights like W1, W2, and overall the bias B, which is a static number, right? But the input is not, the output is not 0 or 1. Instead, it's this formula here, where I think this is a sigma, right? No? What kind of nope, no remember. Yo, it's actually a sigma. Nice. Yeah, so it's the sigma notation. It's called the sigmoid. Sigmoid. Mathematics being funny, and it's defined in this way. Okay. I actually seen this formula before. Wait, I have seen this before. Anyways. I think I've seen this in a class where we did go through electrical signals. I think this is something similar. It's like the C transform or whatever. In a complex plane, I think. Wait, I have to search this up. Transform table, I think. Let me go here. Yeah, here it is. It's this one here. Here. No, this is only in what is it called? It's this is not continuous. It's discrete interval. Because we see this notation here, but it's the same. This is actually the same as this one, I think. Or maybe it's not, because it's e to the power of z, and z is the input. But here is the z. I don't know. I have to look this up. But anyways, the output is the sigma function. Sigma function, it sounds so weird, with the weights, and that is the cross product, so making a big fat point or dot here, multiplied with the input plus the bias. Where the delta, which I cannot write at all. Not that it's a sigma. Sigma is called the sigmoid function. Alright. And is defined by so this is like a very interesting way to write this. This equal sign here is actually saying that it's proven to be equal to this. So it's 100% equal to this equation in terms of mathematics. Very interesting. To put it a little more explicitly, the output of a sigmoid neuron with inputs of infinite amount of inputs and infinite amount of weights and bias is just a static value is equal to this. But this is more like generalization. Or this is actually the generalization that if you input the general amount of inputs, you will essentially get this value here. And so this is just a way to write the exponential way. What this actually means is this whole, I cannot, it's written in LaTeX, so I cannot really ask about anything. And I don't want to talk with the AI assistant. But this here is essentially the C value here. So this is the summation of all the matrix multiplications with the bias as well. And the bias is negative, I think. So this gives us that. I can write this. I will probably write my own document and explain this later, but this is just me. There's a really interesting math. I kind of understand the math as well, which is very interesting. I wrote this wrong. I wrote the summation wrong. And I think... Yeah, so they have moved this minus sign in here, so the bias should actually be positive if it's inside a parenthesis. Okay, at first sight, the sigmoid neurons appear very different to perceptrons. The algebraic form of the sigmoid function makes them opaque, or how do you even pronounce this word? Nope. And forbidding if you're not already familiar with it. In fact, there are many similarities between perceptrons and sigmoid neurons, and the algebraic form of the sigmoid function turns out to be more of a technical detail than a true barrier to understanding. Yeah, that makes sense. To understand the similarity to the perceptron model, suppose that the C is equal to the weight with the cross product of the inputs plus the bias is a large positive number, then e to the power of minus c is equal to almost equal to 0 or close to 0, which makes sense because if you have 1 divided by e to a very large value, then you have basically say for example that the value goes to infinity, then you have 1 divided by something very large, which is super small, which goes down to almost 0. So this is like the limits value. Yeah. So here you basically have, if this value goes to infinity, then this goes to 0. I kind of jumped forward with the explanation. That's my bad. And yeah, just to like make sure that everyone knows, I haven't seen this equation before. This is my first time seeing it, so I'm kind of like discovering what they are explaining by just thinking about it. In other words, when the C is equal to the cross product between W and the weights and the input plus the bias is large and a positive number, then the output from the sigmoid neuron is approximately 1. Wait a minute. So if C is equal to a large positive number, the output of the sigmoid is approximately 1. Yes, because the e to the power of minus z is equal to 0, so 1 divided by 1, which is 1. So that makes sense. Suppose on the other hand that it's a very negative number. Yes, okay, so then it goes to infinity, right? Because this becomes super large, and then you have 1 divided by 1 plus a super large number, which makes it go to infinity. Or makes this go denominator to infinity, and then you have 1 divided by infinity, which is equal to 0. Yeah, or almost equal, approximately 0. So when z is equal to z is equal to not z, z is equal to the weights cross product with the input plus the bias is very negative, the behavior of a sigmoid neuron also closely approximates a perceptron. It's only when the weights cross product between the inputs plus the bias is of the modest size, there's much deviation from the perceptron of the model. So it basically means that if the input is super large in a positive way, we get close to a point where we have almost the same value as a perceptron, and it's also the same in the vice versa scenario. But if we are between those two different scenarios, then we have a very different type of behavior. Okay, that makes sense. What about the algebraic form of the sigmoid function? How can we understand that? In fact, the exact form of sigmoid function isn't so important. What really matters is the shape of the function when plotted. Okay, so this is probably gonna explain what I just explained, I think. Yeah, so if we have, I think this is the, wait, so this is the step function. I actually kind of figured this out already. So this step function here is the same as this one here. It's super fun because this is just from something. This is not even like AI stuff. This is control theory, but it's the same behavior. What? That's incredible. I didn't understand. Oh, this is Chinese, by the way. Anyways, and so the sigmoid function. Do we have a sigmoid function here? I feel like I've seen this somewhere. I am getting too excited for this. Wait a minute. Nope. No, it's not. It's definitely not the same, but I'm getting too excited for this. Now we're coming into probability theory. Okay. Anyways, so the sigmoid function, but I want to understand if these are the inputs or this is the output. I don't understand what this specifically means. This has to be the input, I think. If this is 0, if the input is 0, then we have e to the power of 0, which is equal to 1. And then we have 1 divided by 2, which is 0.5. If we just make like kind of goes there, yeah, then we have 0.5. So this is the output and this is the input. Okay, great. So if we have a very small number, we essentially, for example, -4 in the input, we essentially have 1 divided by e to the power 4, which is super small. No, it's actually big, never mind. So we have a very large number. So it goes close to 0 and then it goes close to 1. But here it may differ, yeah, so this makes sense. Yeah, absolutely. I actually kind of want to write this down because this is very important, I think. But that's good to know. Jesus, I'm terrible at writing. Yeah, I kind of made it pretty decent, I think. And now we're gonna do the step function. So this is I think a closed interval, and this is an interval. So this is how a perceptron works. Okay, that's interesting. I read this wrong. Very nice. I think this is about the middle, I think. And then we have at the 0, we go from 0 to 1 immediately. Which makes sense. So this is a smoothed out version of the step function. If the sigmoid function had in fact been a step function, then the sigmoid neuron would be a perceptron, since the output would be 0 or 1 depending on whether okay. That makes sense. Okay, so if only the sigmoid function would have an output of 0 and 1, it would be the step function, which is also equal to a perceptron. But if we have an arranged interval between values of 0 and 1, we have a sigmoid function that basically behaves like a perceptron in these endpoints here, but in the middle of those endpoints we have a completely different behavior. That's very interesting. Yeah, so if it had been a step function, then the sigmoid neuron would be a perceptron, since the output would be 0 or 1, depending on whether the input, which is the weights with cross products by the inputs, plus the bias, was positive or negative. By using the actual sigmoid function, we get, as already implied, about a smoothed out perceptron. Indeed, it's the smoothness of the function that is the crucial fact, not its detailed form. The smoothness of the sigmoid function means that small changes in the differences or the delta weights in the weights and the delta bias in the bias will produce a small change of the delta output in the output from the neuron. In fact, calculus tells us that the delta output is a small approximate, is well approximated by this one here. So this can be something good to write down as well. But this is also if we just assume that we have a close value to the actual function that we want to accomplish, which basically means that if we are way off with the data, we have a problem, but that's fine. Oh, by the way, I thought this was the delta value, but it's actually a derivative. It's the derivative. Oh, wait, I've seen this equation before. I've actually seen this equation before. Holy shit. This is, I think, the summation of the derivatives of multivariable derivatives, right? In a multivariable calculus. I've seen this equation before. Where the sum is over all the weights and outputs, and yeah, denote the partial derivatives, right? Yeah, this is partial derivatives. This is a general function in multivariable calculus with partial derivatives. Yeah, I've seen this before. Don't panic if you're not comfortable with partial derivatives. I am. I'm sorry to disappoint, but I am. While the expression above looks complicated with all the partial derivatives, it's actually saying something very simple, and which is very good news. Output is a linear function of the changes of the weights and the bias in the weights. In the way, this linearity makes it easy to choose small changes in the weights and biases to achieve any desired small change in the output. So while sigmoid units have much of the same qualitative behavior as perceptrons, they make it much easier to figure out how changing the weights biases will change the outputs. If it is the same shape, if it is the shape of a sigmoid function, which really matters, and it's not exact form, then why use particular form used in equation 3? Where the frick is equation 3? It's here. This is what I write here. In fact, later in the book, we will occasionally consider neurons where the output is a function of the weight cross-product with the inputs plus the bias for some other activation function. Oh, they even use this kind of like notation. The main thing that changes when we use a different activation function is the particular values of the partial derivatives in function 5 changes. This is very good to know. So basically what they say is, if we have a different activation function, which I think in this, if I'm correct, it's the ReLU function, but I might be is the ReLU function an activation function? Let's check this. ReLU is an activation function, question mark. Yes, ReLU is a type of activation function used in neural networks. Great. So it's basically different ReLUs in that sense. So if we use a different ReLU, the weights and biases is gonna change. Some other activation function. And their notation is saying f dot, which basically means that we have some type of function where we don't know the input, but that input is probably gonna determine which type of activation function we actually have. Just so you guys know. The main theme that changes when we use a different activation function is that the particular values of the partial derivatives in the equation 5 changes. So the values in this equation here, which is the partial derivatives of the input and the weight, and also the bias, is gonna change. So they are basically just saying that if we're gonna use a different activation function, the input values and the bias and the weights is gonna change. Like, no shit should look, but it's too good to like highlight that it will change, because when people say activation function, no one really understands what that means. But you basically just change the total environment of the network. That's what an activation function does. It changes the environment of the network. Is that the particular values for the partial derivative where did I put partial derivative derivatives in the equation changes. Equation changes. Nice. Okay, that's good to know. It turns out that we compute those partial derivatives later using the sigmoid function, which will simply with the algebra, simply because exponentials have lovely properties when differentiated. So exponentials. So we are not talking about the e function. I think we are talking about how they use logarithmic values, I think. In any case, the sigmoid function is commonly used in work on neural nets, and it's the activation function we will use most of the time in this book. How should we interpret the output from a sigmoid neuron? Obviously, one big difference between perceptrons and sigmoid neurons is that sigmoid neurons doesn't just output 0 and 1, they can have as output any real number between 0 and 1. So values such as 0.73 and 0.689 are legitimate outputs. This can be useful, for example, if we want to use the output value to represent the average intensity of the pixels in an image input to a neural network, which basically means it is a heat map in that sense. but sometimes it can be a nuisance. Suppose we want to output from the network to indicate either the input image is a 9 or the input image is not a 9. Obviously, it would be easy to do this if the input was a 0 or 1, as in a perceptron. But in practice, we can set up a convention to deal with this. For example, by deciding to interpret any output of at least 0.5 as indicating a 9. And any output less than 0.5 as indicating not a 9. So they are basically just creating a mathematical equal or not equal condition to decide whether the output is a 9 or not. I will always explicitly state that when we are using a convention, so it shouldn't cause any confusion. So exercises, sigmoid neurons simulating perceptions, part 1. Suppose we take all weights and biases in a network of perceptrons and multiply them by a positive constant. Show that behavior of a network doesn't change. It's probably because, wait, so we take all weights and biases. Okay, so we are just moved. Okay, so I'm not gonna like write this down, but I can explain it. So when we have a network of perceptrons, just to make it easy, it probably should be the same functionality as for sigmoid neurons, but we can, let's just take sigmoid neurons. The differences between, I think it's in here. Yeah, so we can technically, I think it's either here or in this equation. I think we have long. Okay, so I think it's probably should be in this equation here, I think. So the differences, so if we multiply 3 on the output, which is the same as multiplying 3 on the on the weights and biases, it doesn't change the differences between the output. And also, if we would multiply by 3, which is a constant value, before we do the partial derivative, the 3 would actually disappear, because it only takes into account the variables, which is the weight and biases and input, but not the constant. So, but just because of this derivative loss, we will remove the number of 3, I think. So in the end, it doesn't really matter. And I think if we just like do this, I think this is gonna have the same answer. I mean, if we just go here and just go into ChatGPT or whatever. And I think I just knocked my mic and just explain this question. So this question is about understanding why scaling all weights and biases in a perception network by a positive constant doesn't change the network behavior. So the output is either 1 or 0. That is not completely... Oh, that's perception basics. Okay, never mind. So that is true. That is very true. So if we scale the weights, we see multiply with the weights, right? So this is basically what it looks like. That is what I said before. Why the behavior is unchanged. Since c is greater than 0, multiplying by c doesn't change the sign. So it doesn't change the sign. That's a good thing. If it were less than 0, then it would be a problematic situation. But then, why is the sigmoid neuron simulating perceptrons section? A sigmoid neuron activation is this function here, which we saw. If c is large and sigmoid becomes steeper, the approximating a perceptron step function is 0 or 1 output. The question is essentially pointing out that perceptron scaling by c greater than 0 has no effect at all on the classification decision. Exactly. But then I might be wrong, because are there any partial derivatives that make the constant not important? Oops. Yes, in the pure perceptron case, there's no need to even talk about partial derivatives because the output is hard threshold. Exactly. For a sigma neuron, we scale with C. Nope, I don't try to study. Or I'm studying, but whatever. When you apply this chain rule, which we did go through before, since C prime is equal to C, or Z prime is equal to Z multiplied with Z, the extra factor C changes shape, so it changes the shape. If C is large, it's close to 0 except near vanishing gradient. Yes. If C is small, the sigmoid function prime is broader and gradients are larger. So in training, C affects gradients magnitude and conventional speed, even though in a pure perceptron, the classification boundary is unchanged. I think for this particular question, I don't think we should probably... I understand why it would change, because the gradient itself would, like, you could see in an area, you would actually increase the area by multiplying by 3, so the training would be different, but I think in this scenario, it doesn't really matter. Suppose we have the same setup as the last problem, network of perceptrons. Why? Ah, okay, so this is only perceptrons. I'm getting a bit tired. I thought it was a sigmoid function. Never mind. So this is basically just, it's basically just this step function here. Okay, it doesn't really matter. With a setup network of perceptrons, suppose also the overall input to the network of perception has been chosen. There we won't need an actual input value. We just need the input to have been fixed. Suppose the weights of the and biases are such that they are not equal to 0. The input is not equal to 0 for the input x to any particular perceptron into the network. Now replace all the perceptrons in the network by sigmoid neurons and multiply the weights and biases by a positive constant C. Show that in the limit as C goes to infinity, the behavior of this network of sigmoid neurons is exactly the same as the network of perceptrons. How can this fail when the input is equal to 0 for one of the perceptrons? Okay, so I have to kind of like understand this correctly. So first of all, we assume that the input is not equal to 0. Okay. And then we have a constant C, which we want, which is a positive number greater than 0. Show that in the limit as C goes to infinity, the behavior of this network of a sigma neuron is exactly the same as the network of perceptron. And can this fail when that the input is equal? Okay, so we are basically gonna show that when C goes to infinity, the behavior of the network of sigmoid neurons is the same as a perceptron. But if the input is 0, then we have to like show why this will fail. So this is basically I think I have the same problem in control theory, but anyways. So I think it goes back to this equation here. So if the input is this here, or the summation, and we multiply by a C constant, then and we also assume that the input is not 0. We actually, I'm not completely sure how this works out. That's a very good question. Let's do this. I have no idea how this works. So this is kind of what I thought about. Yeah. Consider the limit where C goes to infinity. If C goes to the infinity, this will be incredibly small. So that should be equal to 1. Yes. If it's greater, so if Z is greater to 0 and C goes to infinity, that goes to 1. if c is smaller than 0, which basically means that we have no negative sign, and c would go to infinity, this will increase in size, this value here, which will put the whole value to 0, because we have 1 divided by infinity, which is 0. And then if c is equal to 0, we have c is, so e to the power of 0 is equal to 1. So we have 1 divided by 1 plus 1, which is 1 divided by 2, which contradicts the step function itself, because then we basically say that if the input here is, which is here by the way, if the input here is 0, we should have an output of 0.5, which in this function here we don't have, but in this function we have. So this contradicts the behavior of a perceptron compared with the sigmoid function. That makes so sense. Yeah, I'm gonna write this down actually. It's a really good way to think about it. I'm gonna write this down. This is good. This is really good. I'm gonna write down the question first. I think that is the most important thing to do. But there we can see that now architecture of neural networks. That's pretty awesome. Okay. So first write down the question. I'm gonna highlight this question because this question was so good, actually. If you want this to be explained, I'm currently just writing down everything so I can document this further. But if you want to have an explanation of why this question is so good, roll back the video and watch it because it was very nice. And I think my... Okay, so I'm gonna change pen because this pen is garbage. Now someone is calling me for some reason. I'm gonna call him back later. It was one of my friends. So I just suppose all... Jesus, I just have this wrong. Suppose also that the overall input to the network of perceptrons has been chosen. All right. We won't need the actual input value we just need the input to be fixed, right? To have been fixed. Okay, nice, that makes sense. To have been fixed. Suppose the weights and biases are such that the weights cross product between the inputs plus the bias is not equal to 0 for the input x. To any particular, let's see, particular perceptron it's a plural perceptrons in the network. That wrong, but that's a terrible erase bit. In then all perceptrons. Wait, where did I? To any perceptron in the network. Now replace all the perceptrons in the network by sigmoid errands. And multiply the weights and biases by a positive number. Positive constancy, which is greater than 0. Yeah. Show that in the limits as c goes to infinity, the behavior of this network of perceptrons. Same. Wait, network of the behavior of this network of sigmoid, not perceptrons, sigmoid. Neurons is exactly the same as the network of perceptrons. How can this fail? When the input is equal to 0. For one perceptron, okay. One of the perceptrons, right? Right. Now we have the answer, which ChatGPT gave us. Which is basically so if we scale the weights and biases, we scale the input as a whole, which basically means that the sigmoid function will be scaled as well. Which makes sense. So if the z value is bigger than 0 and the c is going to infinity, the end expression becomes 1. Right. There we go. Makes sense. if c is less than 0, as c goes to infinity, we get that the e to the power of minus cz is going to infinity as well, which basically makes the sigmoid function going to 0. And if we have that the input, which is z, is equal to 0, we get that, and it doesn't really matter what c is going to, because infinity multiplied by 0 is actually 0. Then we get that the sigmoid function is actually going to be equal to the sigmoid function where the input is also to 0, which is also equal to 0.5 for every c that we input, right? Which doesn't make sense for a discrete interval of values. But for a continuous one, it does make sense. So that's good to know. Now we know. So we have answered this question here. Let's go to the architecture of neural networks. So in this next section, I will introduce a new neural network that can do a pretty good job classifying handwritten digits. In preparation for that, it helps to explain some terminology that lets us name different parts of the network. Suppose we have the network, this kind of network. As mentioned earlier, the leftmost layer in this network is called the input layer. So this is the input layer. The neurons within the layer are called the input neurons. The rightmost or output layer contains the output neurons. So I'm actually gonna paint this out just to, have the conventions with us. Yep. So what we can see here now is that every path or weight is going to each other. So this neuron here, or the input neuron here, will have the 4 connections. This will have 4 connections, and this will have 4 connections. And this one will have in total 4 connections as well, but 3 of them are inputs and 1 of them are outputs, and this will have 4 connections. So all of these neurons technically have 4 connections, but the connections might differ, right? Yeah, just because it's funny, I don't think it's gonna matter too much, I think, but it's good to know. And now we're gonna have output neuron. And then we have the output itself. Okay. So here we're gonna call the leftmost layer is equal to the input layer. The middle, I think they call it input layer. The neurons within the layer, so middle layer. Is equal to called input neurons. And the rightmost layer, I think they call it. Is called hidden layer. What? No. So the middle layer is actually called hidden layer, by the way. So this is actually, they use it different. I think they use different terminology. Right? The middle layer is called hidden layer since the nearest is the layer right? Neither up. So it's hidden layer. So input layer, hidden layer, and output layer. Yeah. And I think I said that before. Yeah. So as mentioned earlier, the leftmost layer in this network is called the input layer, and the neurons within the layer are called input neurons. The rightmost or output layer contains output neurons, or in this case, a single output neuron. The middle layer is called hidden layer, which, since the neurons is this layer, are neither inputs or outputs. The term hidden perhaps sounds a little mysterious. The first time I heard the term, I thought it must have some deep philosophical or mathematical significance, but it really means nothing more than not an input or output layer. The network above just has this single hidden layer, but some networks have multiple hidden layers. For example, following 4 layers networks has 2 hidden layers. Yeah, makes sense. So here we have like another type of network. I gotta write this down as well. But I actually think I will stop here and yeah, do this by myself. So yeah, thank you guys for watching and have a great day.